We are continuing with section 11.10, and in this section we learned how to create or how to find the Taylor series or Maclaurin series of a given function. So here I have written put together the three functions famous that you should know how to find their Taylor or Maclaurin series, and also that at any point. So not only that you should know how to get it, but also you should know what the kind of remember the nth term of the polynomial of the series, Taylor series. So here e to the x is equal to summation n is equal to 0 to infinity 1 over n factorial x to the n. And we have it in the expanded or the open form as well. Then sine x, I showed you that one. So it involves odd integers, so odd powers, and then the factorial in the denominator is also odd number. Cosine x, this is a series I expect you guys to find on your own, just following the work I showed you for the sine x. Now, because we are finding the Maclaurin series here, so you notice that in the sine function, the odd powers are left. We are not getting the even powers of x, because the even derivative, when evaluated at 0, some terms are 0, because sine of 0 is 0. So whenever you have the derivative contains the sine x, the derivative is 0, so the term is 0. So there are some terms which are not in some powers of x we are not seeing. In the same way, only odd powers of x we can see in the sine series. In the cosine, we will see the ones which are even. Same way, but now they will be even powers and alternate signs. Okay, so now that we have these known, we can find the Maclaurin series for some other functions, a combination of these functions. For example, example 4 here says find the Maclaurin series for x times sine x. So for this one, we are now going to start from the beginning. F of x equal to x sine x, then find f prime of x, and you see this is a product rule, and then in the product rule, if we keep on taking the derivatives, the number of terms become more and more, so it will be very cumbersome to do that. So we use a smart procedure or smart trick, that we have the sine series written up there. So x sine x will be just to multiply the series by x. Now x is not depending on n, so an x can be pulled inside the summation sign. So we get So what do we get? So I am going to write this first. So x into this series, x minus 1 over 3 factorial x cubed over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the 7 plus dot dot dot. So now distribute and we get x squared minus 1 over 3 factorial x to the fourth then we have so we had x squared plus 1 over 5 factorial x to the 5. Actually, I am multiplying x to the 6 minus 1 over 7 factorial x to the 8 plus. So in the closed form, this will be summation and it's from 0 to infinity. Now actually I can do it from n is equal to 1 to infinity. Or even x n is equal to 2 to infinity. Because the first term is x squared. The factorials at the bottom are the same, but the power is now even. So how will you write that? Negative 1 raised to n for now. And then we have x raised to the power 2n. And then divided by. So this will be 2n. Now we have to think about it. Will it be 2n plus 1 or 2n minus 1? So if you look at the second term, we have 3 factorial down here and on the power is 4. So it will be at the bottom 2n minus 1 factorial. So the change is not coming in the factorial in the number. The change is coming in the power of x. Okay, so now we check is it okay, because remember the power of x was 2n plus 1. So we are bringing in one more x, so it should be 2n plus 2. And that that means 2 times n plus 1. This power is also same as 2 times n plus 1. So this is what we have to check from the by taking term by term. So when n is, so it looks like n has to start at 1. Let's check again. So negative 1 to the n, and if n is 1, this will give me first term negative, which I don't want. We want the first term to be positive. So we can take n plus 1, power of 1. Okay, let me write it clearly. summation n equals something to infinity, and in here -1. Again, what power we have to put there, we'll see. Then we have x raised to the power. So if I put 1 here, so I can say 2n, and then at the bottom, so if this is 2n, so the first one will be when n is 2, this will give me incorrect 2n minus 1 factorial. So when x is 1, x, we get x square, and at the bottom 2 minus 1 is 1. So we will get the x square term but with a negative sign, so I have to add 1 here. That is the Maclaurin series for x times sine x. Now example 5 says find the Maclaurin series for cosine x squared. So again, we already know the cosine series. What we have to do is just, in place of x, I have to replace it by x squared. So cosine x square will be equal to, so it's right here, 1 minus 1 over 2 factorial into x square whole square plus 1 over 4 factorial x square whole to the 4, then minus 1 over 6 factorial x square whole raised to the power 6, and plus so on. So this gives us 1 minus 1 over 2 factorial x to the 4 plus 1 over 4 factorial x to the 8 minus 1 minus 1 factorial, sorry, minus 1 over 1 over 6 factorial x raised to the power 12, and then plus dot dot. So what is the closed form? Summation n is equal to 0 to infinity sorry about that sound. Find the first, okay, so we have to finish this. N is equal to 0 to infinity, so -1 raised to n is fine, divided by, so down at the bottom we have factorial, so 2 factorial, 4 factorial, 6 factorial, and so on. So can I say 2n factorial? Note here, if we start at 0, then 2n factorial becomes 0 factorial, which is 1. We are okay with that. 0. So we will end up getting a 1. And x raised to the power 2n. So that is the series for the cosine of x squared. Now sometimes, okay, so example number 6 says find Maclaurin series for e to the x times cosine x. And then it says find the first 4 terms. Now note here, e to the x is 1 plus x square over 2 factorial plus x3 over 3 factorial x cube over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial, and so on. And the cosine x we just saw is 1 minus 1 over 2 factorial x square plus 1 over 4 factorial x 4 plus 1 over minus 1 over, so alternate signs, minus 1 over 6 factorial x to the 6 plus dot dot dot. So now how do we multiply these? Because these are the infinite series, so we cannot do infinite multiplications. That's why the question says find the first 4 terms. So what we do is we try to multiply out and then see how many terms we need in order to have the 4 terms, and what will be the highest power on the variable. So we multiply using our techniques that we have learned in algebra. It's a horizontal multiplication. So first I am going to take one term from this first polynomial. This is e to the x, remember, and this is cosine of x. We are multiplying them. So I take one element or one term of the cosine and I multiply with the one term of e to the x multiplied with at least 4 terms of the cosine x. So it gives me 1 into 1 is 1, so I get the terms as they are. Plus da 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 da, and then in the next line I'm going to take the next term in e to the x and multiply it with all the terms there, and I'm going to put them over here. Plus x into 1 is just x, x into 1 over 2 factorial into x square will make it minus 1 over 2 factorial x squared, or does it become x cubed? Yeah, it's x squared and it gets multiplied by x, so it's cubed, plus x multiplied by 1 over 4 factorial x to the 4 over 4. 4 is x to the 4, x to the 5, because we multiply by the x. x to the 5, and then minus 1 over 6 factorial x to the 7. So then we can take the next number, x square over 2. Actually, from here we can make an idea. So we have 1. The next term is the x, which is over here. So we already have 1 plus x minus 1/2 x squared (1 plus x minus 1/2 x squared), and then x cubed term, 1 over minus 1 over 2 factorial x cubed. So these are 4 terms. But now we have to make sure that we are not leaving anything. So we have to go up to 3 power 3 maximum, because that will give us 4 terms. So we have to now check that we are not getting any of these powers from any other product. So because we have x squared over 2 with which we are going to multiply, and we multiplied only the first one, which gave us 1 over 2x cubed. So these are the first 4 terms, although we have here going on and on and on. Now if I take this third term, even if I multiply it with the first number here, 1, that is more than what we need. So the first 4 terms goes. Next example. So it says find the Taylor polynomial of degree 3. Sometimes they ask you to find the polynomial, not the series. So in this case, degree 3 means x cube, x to the 3rd power. Okay, let's start. So a is 16 in this case. So f of x is equal to square root of x, which you know is 1/2, and derivative will be, because I can write it as x to the 1/2. So derivative will be 1/2 x to the negative 1/2 f double prime of x will be, so we already have 1/2 here, then it will come the negative 1/2 x to the negative 3/2, because we subtract 1 from the power, and f triple prime or f3 of x is 1 over 2, negative 1 over 2, and then negative 3 over 2. Okay. So we have to evaluate it at 16. So I get f of 16 will be equal to square root of 16, which is equal to 4. F prime of 16 will be 1/2 square root at the bottom of 16. So 1 over 8 f double prime is 16 will be equal to 1 over 2 times negative 1 over 2. Actually, there is another way to look at it. We will do that in a few minutes. Negative 1 over 2 times negative 3 over 2 No, not yet. 3 over 2 is coming in the next one. It's 1 over square root of 16 cube, or you can say 16 raised to 3 over 2 in the denominator. Which is equal to 1 over 2 negative 1 over 2 times 1 over, so 16 square root of 16 is 4, 4 cube is 64. Then f3 third derivative evaluated at 16 will give me, we have 1 over 2, negative 1 over 2, then we have negative 3 over 2, and then x at the bottom, x raised to the, forgot to put the x term, negative 5 over 2. So 5 over 2. 16. 16 raised to 5 over 2. So that this gives me 1 over 2, negative 1 over 2 times negative 3 over 2 times 1 over, now 6, half of 16 is 16 square root is 4, and 4 raised to 5 is 64 into 16. Sixteen fours are 64. 4 comes here, 6 goes up there. 16 6 are 96. 96 plus 6 is 112. So 124. Okay. So now we will write the polynomial. So polynomial comes right, the square root of x f of 16 was 4. Now note here the next derivative, first derivative is gave us 1 over 8. Plus y plus, let's see, because we have two negative signs here, this one and this one, negative negative positive. No, there's only one negative sign. Okay, negative, so this gives me negative 1 over 4, and then 1 over 64 into 4 is 256 minus 1 over 256. X minus 16. Next term we have the two negative signs. So plus 3 over 2 into 2 into 2 is 8. And then we have 1 over 2 and 124 as well. And x minus 16 whole square. The square will come here and then divided by 2 factorial. This will be cube divided by 3 factorial. Now 2 factorial is just 2 and 256 into 2, so I have 1 over 256 into 2, 500 something. $512 x minus 16 whole square plus, so we have 124 into 8. Now 3 factorial can be written as 3 into 2 into 1. This 3 and this 3 cancel out and we are left with 2 here in the bottom. So 2 into 8 into 124. Into 8 into 124. 1984. Okay, now notice here, since I multiplied these numbers out, now I cannot really see the pattern here. But let's so we have to write only the up to cube for it's a polynomial of degree 3. So here because we don't have to write the common the general term, because we are not expanding it to infinity. We are only writing the first 4 terms. So that's it. You can simplify. You don't need to have a formula here. So this is how we do the series. Now, just one thing I wanted you to note. I did an example where our function was ln of x, and you were to evaluate it as x is equal to one, which is actually a is equal to 1. And we started with f prime x, which is equal to 1 over x. Then the next will be double prime x will be negative 1 over x square at the bottom, actually x to the negative 1. So this is negative 1 x to the negative 2 and so on. Now sometimes it could be that you are given f of x is 1 over x and the rest you go from there now. So but notice here because our ln of 1, our f of a was 0, so our f prime of 1 was the first non-zero term. So you can be given a question where they ask you to find the power, the Taylor series of f of x is equal to 1 over x. So note here, we are starting at this step. We are starting at this step. So if you notice, you will get the same or similar Taylor series as we had for ln of x. Okay, so that is all for the Taylor polynomial, Taylor and Maclaurin polynomials, or Taylor and Maclaurin series.